So let us start with a new topic, which is process synchronization. So here are the objectives which we'll be undergoing in this chapter. First is to introduce the critical section problem, whose solution can be used to ensure the consistency of shared data. Second, to present both software and hardware solutions of the critical section problem. And last but not the least, to introduce the concept of atomic transaction and describe mechanisms to ensure atomicity. So first let us check the background. So in chapter 3, we developed a model of a system consisting of cooperating sequential processes or threads, all running asynchronously and possibly sharing data. We illustrated this model with the producer-consumer problem, which is representative of operating system, specifically in the earlier chapter. We described how a bounded buffer could be used to enable processes to share memory. Now let us return to our consideration of the bounded buffer. As we pointed out, our solution allows at most buffer size minus 1 items in the buffer at the same time. Suppose we want to modify the algorithm to remedy this deficiency. One possibility is to add an integer variable counter, initialized to 0. Counter is incremented every time we add a new item to the buffer and is decremented every time we remove one item from the buffer. Now here is the code for the producer process and can be modified as follows, and here is the code for the consumer process. Although both the producer and consumer routines are correct separately, they may not function correctly when executed concurrently, or in the sense when both of them are executed together. As an illustration, suppose that the value of variable counter is currently 5 and that the producer and the consumer processes execute the statement counter plus plus and counter minus minus concurrently. Following the execution of these two statements, the value of the variable counter may be 4, 5 or 6. The only correct result through is counter equal to 5, which is generated correctly if the producer and consumer were executed separately. We can show that the value of counter may be incorrect as follows. Note that the statement counter plus plus may be implemented in machine language on a typical machine as this. When register 1 is a local CPU register, similarly the statement counter minus minus implemented as follows, which you can see over here, where against register 2 is a local CPU register, even though register 1 and register 2 may be the same physical register as accumulated. Say that the contents of this register will be saved and restored by the interrupt handler. The concurrent execution of the counter plus plus and counter minus minus is equivalently to a sequential execution where the lower level statements are presented previously are interleaved in some arbitrary order. One such interleaving is over here, which you can see. So notice that we have arrived at the incorrect statement counter equal to 4, indicating that counter buffers are full, when in fact 5 buffers are full. If we reverse the order of the statement at T4 and T5, we could arrive at the incorrect state counter minus minus 6. We would arrive at the incorrect state because we allowed both processes to manipulate the variable counter at once. A situation like this where several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place, is called a race condition. To guard against the race condition above, we need to ensure that only one process at a time can be manipulating the variable counter. To make such a guarantee, we require that the processes be synchronized in some way. Situations such as the one just described occur frequently in OS as different parts of the system manipulate resources. Clearly, we want the resulting changes not to interfere with one another. Because of the importance of this issue, a major portion of this chapter is concerned with process synchronization and coordination. So in the previous part, you have seen that I have just read this whole concept thoroughly. So now I'll just explain it in brief. So what we are trying to say is there might be two programs, like program 1 and program 2, which may execute separately at a proper value. Whereas if you merge both of them and create a single code, there are chances that the code may not be executed, which you can see over here. Over here, it explains why the code cannot be executed correctly. This is the example of consumer producer problem which we had discussed in chapter number 3. This whole thing is just the description of what I have explained just now.
The critical section problem considers system consisting of in process P0, P1, Pn-1. Each process has a segment of code called as critical section, in which the process may be changing common variables, updating a table, writing a file, and so on. The important feature of this system is that when one process is executing in its critical section, no other process is to be allowed to execute in its critical section. That is, no two processes are executing in their critical sections at the same time. The critical section problem is to design a protocol that the processes can use to cooperate. Each process must request permission to enter its critical section. The section of code implementing this request is the entry section. The critical section may be followed by an exit section. The remaining code is the remainder section. The general section of a typical process PI is shown in figure 6.1. The entry section and exit section are enclosed in boxes to highlight these important segments of code. A solution to the critical section problem must satisfy the following three requirements. Mutual exclusion. If process PI is executing in its critical section, then no other process can be executing in their critical sections. Progress. If no progress is executing in its critical section and some process which to enter the critical sections, then only those processes that are not executing in their remainder sections can participate in the decisions on which will enter its critical section next. And this selection cannot be postponed indefinitely. Bounded waiting. There exists a bound or limit on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. We assume that each process is executing a non-zero speed. However, we can make no assumptions concerning the relative speed of the end processes. At a given point in time, many kernel mode processes may be active in the operating system. As a result, the code implementing an operating system, kernel code, is subjected to several possible race conditions. Consider as an example a kernel data structure that maintains a list of all open files in the system. This list, this list must be modified when a new file is opened or closed, adding the file to the list or removing it from the list. If two processes were to open files simultaneously, the separate updates to this list could result in a race condition. Other kernel data structures that are prone to possible race conditions include structures for maintaining memory allocation, for maintaining processes list, and for interrupt handling. It is up to kernel developers to ensure that the operating system is free from such rare conditions. Two general approaches are used to handle critical sections in operating system. First one, preemptive kernels, and second one, non-preemptive kernels. A preemptive kernel allows a process to be preempted while it is running in kernel mode. A non-preemptive kernel does not allow a process running in kernel mode to be preempted. A kernel mode process will run until it exits kernel mode blocks or voluntarily yields control of the CPU. Obviously, a non-preemptive kernel is essentially free from race conditions on kernel data structure, as only one process is active in its kernel at a time. We cannot say the same about non-preemptive kernel, so they must be carefully designed to ensure that shared kernel data are free from race conditions. Preemptive kernels are especially difficult to design for 5MP architectures, since in these environments it is possible for two kernel mode processes to run simultaneously on different processes. Why then would anyone favor a preemptive kernel over a non-preemptive one? A preemptive kernel is more suitable for real-time programming, as it will allow a real-time process to preempt a process currently running in the kernel. Furthermore, a preemptive kernel may be more responsive, since there is less risk that kernel mode process will run for an arbitrarily long period before relinquishing the processes to waiting processes. Of course, this effort can be minimized by designing kernel code that does not behave in this way. Windows XP and Windows 2000 are non-preemptive kernels, as is the traditional Unix kernel. Prior to Linux 2.6, the Linux kernel was non-preemptive as well. However, with the release of the 2.6 kernel, Linux changed to the preemptive model. Several commercial versions of Unix are preemptive, including Solaris and IRIX.
Peterson's solution. We illustrate a classic software-based solution to the critical section problem known as Peterson's solution. Because of the way modern computer architecture perform basic machine language instructions such as load and store, there are no guarantees that Peterson's solution will work correctly on such architectures. However, we present the solution because it provides a good algorithmic description of solving the critical section problem and illustrates some of the complexities involved in designing software that address the requirement of mutual exclusion, progress, and bounded waiting requirements. Peterson's solution is restricted to two processes that alternate execution between their critical section and remainder section. The processes are numbered P0 and P1. For convenience, when presenting P, we use Pj to denote the other process, that is j equals 1 minus I. Peterson's solution requires two data items to be shared between the two processes. The variable turn indicates whose turn it is to enter its critical section. That is, if turn equal I, then process Pi is allowed to execute in its critical section. The flag array is used to indicate if a process is ready to enter its critical section. For example, if a flag I is true, this value indicates that Pi is ready to enter its critical section. With an explanation of this data structure complete, we are now ready to describe the algorithm. To enter the critical section, process Pi first set flag I to be true and then set turn to the value j, thereby asserting that if the other process wishes to enter the critical section, it can do so. If both processes try to enter at the same time, turn will be set to the both I and j at roughly the same time. Only one of these assignments will last. The other will occur but will be overwritten immediately. The eventual value of turn decides which of the two processes is allowed to enter its critical section first. We now prove that this solution is correct. We need to show that first one, mutual exclusion is preserved. Second one, the progress requirement is satisfied. Third, the bounded waiting requirement is met. To prove property, we note that each PI enter its critical section only if either flag j equal to false or turn equal to I. Also note that if both processes can be executing in their critical section at the same time, then flag 0 equal to flag 1 equal to true. These two observations imply that P0 and P1 could not have successfully executed their while statement at about the same time. Since the value of turn can be either 0 or 1 but cannot be both. Hence one of process say Pj must have successfully executed the while statement whereas Pi had executed at least one additional statement turn equal to j. However, since at the time flag j equal to true and turn equal to j and this condition will persist as long as pj is in critical section, the result follows mutual exclusion is preserved. To prove property 2 and 3, we note that a process P can be prevented from entering the critical section only if it is stuck in while loop with a condition flag j equal to true and turn equal to j. This loop is only one possible. If pj is not ready to enter the critical section, then flag j equal to false and pi can enter its critical section. If pj has set flag j to true and it's executing in its while statement, there either turn equal to I and turn equal to j. If turn equal to I, then pi will enter the critical section. If turn equal to j, then pj will enter the critical section. However, once pj exits its critical section, it will reset flag j to false, allowing pi to enter its critical section. If pj resets flag j to true, it must also set turn to I. Thus, since pi does not change the value of variable turn while executing the while statement, pi will enter the critical section after at most one entry by pj.
Synchronization hardware. We have just described one software based solution to the critical section problem. In general, we can state that any solution to the critical section problem requires a simple tool, a lock. Race conditions are prevented by requiring that critical regions be protected by locks. That is a that is, a process must acquire a lock before entering a critical section. It releases the lock when it exits the critical section. This is illustrated in figure 6.3. All these solutions are based on the premise of locking. However, as we shall see, the design of such locks can be quite sophisticated. Hardware features can make any programming task easier and improve system efficiency. In this section, we present some simple hardware instructions that are available on many systems and show how they can be used effectively in solving the critical section problem. The critical section problem could be solved simply in a uniprocessor environment if we could prevent interrupts from occurring while a shared variable was being modified. In this manner, we could be sure that the current sequence of instruction would be allowed to execute in order without preemption. No other instructions would be run, so no unexpected modifications could be made to the shared variable. This is the approach taken by non-preemptive kernels. Here, the definition of the test and set instruction, and this is mutual exclusion implementation with test and set. This message passing delays entry into each critical section and system efficiency decreases. Also consider the effect on a system clock if the clock is kept updated by interrupts. Many modern computers system therefore provide special hardware instruction that allows us either to test and modify the content of word of to swap the content of two words automatically. That is one uninterruptible unit. We can use these special instructions to solve the critical section problem in a simpler manner. The test and set instruction can be modified as shown in figure 6.4. The important characteristics is that this instruction is executed automatically. Thus, if two test and set instructions are executed simultaneously, they will be executed sequentially in some arbitrary order. If the machine supports the test and set instruction, then we can implement mutual exclusion by declaring a Boolean variable lock initialized to false. The swap instruction, in a contrast to the test and set instruction, operate on the contents of two words. It is defined as shown in figure 6.6. Like the test and set 0 instruction, it is executed automatically. If the machine supports the swap instruction, then mutual exclusion can be provided as follows. A global Boolean variable lock is declared as is initialized to false. Here, the definition of the swap instruction. And this is mutual exclusion implementation with swap instruction. Another algorithm using the test and set instruction that satisfies all the critical section requirements. The common data structures are Boolean waiting array of n, Boolean lock. These data instructions are initialized to false. To prove that the mutual exclusion requirements is met, we note that process PI can enter its critical section only if either waiting I false or key false. The value of key can become false only if the test and set is executed. The first process to execute the test and set will find key equal to false. All other must. Here, bounded waiting mutual exclusion with test and set. To prove that the progress requirement is met, we note that the arguments presented for mutual exclusion also apply here, since a process existing the critical section either set lock to false or sets waiting to false. Both allow a process that is waiting to enter its critical section to proceed. To prove that the bounded waiting requirement is met, we note that when a process levels its critical section, it, it scans the array waiting in the cyclic order. It designates the first process in this order, that is the entry section. For hardware designers, implementing automatic test and set instruction on multiprocessor is not a trivial task. Such implementations are discussed in this chapter.
Semaphores. Semaphores are synchronization tools used to manage access to shared resources in concurrent programs. A semaphore is an integer variable that can only be accessed using two atomic operations, wait and signal. The wait operation decrements the semaphore value, and if it becomes negative, the process is blocked until the semaphore becomes positive. The signal operation increments the semaphore value, potentially releasing a waiting process if the value becomes non negative. The critical section problem can be solved using semaphores where processors can enter the critical section only when the semaphore value is positive and exit by releasing a semaphore. Usage. Mutex. The shared binary semaphore named mutex is initialized to 1. The purpose of this semaphore is to provide mutual exclusion, allowing only one process to enter the critical section at a time. Critical section. Each process P follows a loop structure with the condition while true, which means it will keep executing indefinitely. Before entering the critical section, the process performs a wait operation on the mutex semaphore to check if it can access the critical section. Wait operation. The wait operation decrements the value of the semaphore. If the value is already 0, indicating that another process is in the critical section, the process will be blocked until the semaphore value becomes 1. When the other process exits the critical section and releases the mutex. Signal operation. After executing the critical section, the process performs a signal operation on the mutex semaphore, incrementing its value to 1, thus allowing another waiting process to enter the critical section. Implementation. Semaphore type. The implementation uses a binary semaphore, also known as mutex lock, named mutex. Binary semaphores can only have values 0 and 1, making them ideal for providing mutual exclusion. Critical section. Each process P follows a loop structure with the condition while true. Inside this loop, the process attempts to enter the critical section by performing a wait operation on the mutex semaphore. The critical section is the code enclosed between the waiting mutex and signal mutex statements. Wait operation. The wait operation decrements the value of the semaphore if the value is 1, mutex is available. The process proceeds to enter the critical section. Otherwise, if the value is 0, another process is in the critical section. The process is blocked until the semaphore value becomes 1. Signal operation. After executing the critical section, the process performs a signal operation on the mutex semaphore, incrementing its value back to 1. This signals other waiting processes that they can now enter the critical section. Deadlocks and starvation. Deadlocks. A deadlock occurs when two or more processes are waiting indefinitely for an event that can only be caused by one of the waiting processes. In the given example, the processes P0 and Pi are deadlocked because each is waiting for the other to execute a signal operation. Semaphore and waiting queue. Semaphores are used to control access to shared resources. When multiple processes need access to a shared resource, they may be put in a waiting queue to wait for their turn to acquire the semaphore. Deadlock state. A set of processes is in a deadlock state when every process in the set is waiting for an event that can be caused only by another process in the same set. In the given example, P0 and Pi are in a deadlock state since each is waiting for the other to release the semaphore. Resource acquisition and release. Deadlocks mainly occur due to improper synchronization of resource acquisition and release. When processes do not release resources properly, other processes may be blocked indefinitely. Starvation. Starvation is another related problem where a process is unable to proceed and make progress because it is constantly being bypassed by the other processes. In the context of semaphores, indefinite blocking may occur if processes are added and removed from the semaphores waiting queue in lasting first out LIFO order. This can cause some processes to wait indefinitely. Dealing with deadlocks. Deadlock prevention, avoidance, and detection are different techniques used to address the deadlock problem in operating system. These techniques aim to ensure that deadlocks do not occur or are resolved when they do.
Classic problems of synchronization. In this section, we present a number of synchronization problems as examples of a large class of concurrency control problems. These problems are used for testing nearly every newly proposed synchronization scheme. In our solutions to the problems, we use semaphores for synchronization. The bounded buffer problem. It is also known as the producer consumer problem, is a classic synchronization problem in computer science and operating systems. It involves two types of processes: producers that produce data and place it into a shared buffer, and consumers that retrieve and process the data from the buffer. The key challenge in the bounded buffer problem is to ensure that the producers do not add data to a full buffer and that the consumers do not retrieve data from an empty buffer. This requires synchronization and coordination between the producers and consumers to prevent race conditions and other concurrency issues. The buffer is of fixed size, meaning it can only hold a limited number of items at any given time. When the buffer is full, the producers must wait until there is a space available to add more data. Similarly, when the buffer is empty, the consumers must wait until new data is available to retrieve and process. Various synchronization mechanisms such as semaphores, mutexes, or monitors can be used to implement solutions to the bounded buffer problem and ensure proper coordination between the producers and consumers. By employing these mechanisms, developers can prevent data corruption, deadlock, or other concurrency related problems and create efficient and reliable concurrent systems. The readers writers problem. It is another classic synchronization problem in computer science and operating systems. It involves multiple readers and writers accessing a shared resource such as a file or a database. The goal is to devise a solution that allows concurrent access by multiple readers but ensures that only one writer can access the resource exclusively at a time. The main challenges in the reader writers problem are as follows. Readers can access the shared resource simultaneously without any conflicts. Only one writer can access the shared resource exclusively at any given time. When a writer is modifying the resource, no other readers or writers should have access. Writers must have priority over readers to prevent writer starvation. Different solutions can be devised to address these challenges using synchronization mechanisms like semaphores, mutexes, or monitors. A common approach is to use a read write lock, also known as multiple reader single writer lock. The read write lock allows multiple readers to acquire the lock concurrently, but when a writer wants to access the resource, it must obtain an exclusive lock, preventing any other readers or writers from accessing it until the writer is done. Implementing a well designed readers writers problem solution ensures proper synchronization and maintains data integrity while optimizing the usage of shared resource in concurrent systems. The dining philosopher's problem. It is a classical synchronization problem that highlights the challenge of resource allocation and deadlock avoidance in a concurrent system. It is named after a scenario where a group of philosophers sit around a circular table with a bowl of rice and a single chopstick between each pair of philosophers. Each philosopher alternates between thinking and eating. To eat, a philosopher needs two chopsticks, one on their left and one on their right. The main challenges in the dining philosopher's problem are as follows. Avoid deadlock. If all philosophers simultaneously pick up their left chopstick, they will be unable to pick up their right chopstick, leading to a deadlock situation where none of them can eat. Avoid starvation. If one philosopher keeps waiting for both chopsticks to become available, they may starve while others keep eating. To solve the dining philosopher's problem, various synchronization techniques can be used, such as semaphores, mutexes, or monitors. One common solution is to use a semaphore representing the number of available chopsticks. Philosophers can pick up chopsticks only if both their left and right chopsticks are available, else, they must wait until the necessary chopsticks are available. This solution ensures that at most one philosopher can pick up both chopsticks at the same time, preventing deadlock. Additionally, it provides fairness by allowing all philosophers to have an equal chance to eat, thus avoiding starvation. By employing suitable synchronization mechanisms, the dining philosopher's problem can be effectively solved, showcasing the importance of proper coordination and resource management in concurrent systems.
Synchronization example. Now, we next describe the synchronization mechanism provided by the Solaris, Windows XP and Linux operating system, as well as the Thread API. We have chosen these systems because they provide a good examples of different approaches for synchronizing the kernel, and we have included the Thread API because it is widely used for thread creation and synchronization by developers on Unix and Linux systems. As we will see in this section, the synchronization methods available in these differing systems vary in subtle and significant ways. The first, synchronization in Solaris. In Solaris, synchronization is crucial to ensure proper coordination and prevent a conflict between concurrent processes and threads. Mutex are used to protect a critical section of a code by allowing only one thread at a time to access the shared resources. Solaris provide various types of mutexes, such as adaptive mutexes and error checking mutex. Semaphores are used to control accesses to shared resources by maintaining a code and representing the number of available resources. Thread can acquire and release the semaphores to regulate access to critical sections. Condition variables are used in a conjunction with mutexes to create more sophisticated synchronization pattern. Solaris provide various system calls and libraries function for managing thread synchronization. Solaris offer a set of thread-safe library functions that can safely used in threads applications. Proper synchronization can also involve setting thread priorities and managing the scheduling policy to control the execution order or threads and prevents a priority invention. And second one, that is synchronization in Windows XP. Keeping in that mind that the information might be outdated, and it is always recommended to refer to the official Microsoft documentation for the most up-to-date information. Windows XP includes a built-in utility called a briefcase for file synchronization. We can also use briefcase to keep files and folders in a sync between two different locations, such as local drive and the remote storage drive. Windows XP supports offline files, which allows you to work with the network files even when you disconnected from the network. When enabled, the systems will automatically synchronize files between the local cache and the network share when you reconnect to the network. A relation exists between the state of a dispatcher object and the state of a thread. When a thread blocks on the non-signaled dispatcher object, its state changes from ready to waiting and thread is placed in waiting queue for the object. When the state of this dispatcher object moves to the signal, the kernel checks whether any thread are waiting on the object. If so, the kernel moves to a thread or possibly move threads from the waiting thread to the ready state, where they can resume executing. The number of threads the kernel select from waiting queue depend on the type of the dispatcher object it is waiting on. The kernel will select only one thread from the waiting queue for the mutex, since the mutex object may be owned by only a single thread for an event object. The kernel will will select all threads that are waiting for the event. Here is the diagram for mutex dispatcher object. And now synchronization in Linux. In Linux, synchronization is crucial to manage a concurrent access to shared resources and prevent data inconsistencies and race conditions among multiple programs, processes, or threads. Here um, mutual exclusion. Mutex is a synchronization primitive and allows only one process or thread to access shared resources at a time. It ensures the inclusive access, preventing multiple processes from modifying data stimulation. Semaphores are integral variables used to control access shared resources. They can also use to implement both mutual exclusion and limited access. Locks are mechanism used for enforced mutual exclusion. They can also implemented as a mutexes, spin locks or reader write locks depending on a specific requirements. Spin locks are busy waiting locks that continuously try to acquire the lock in it becomes available. They are suitable for the scenarios where the locks is expected to be held in the short duration. Linux uses an interesting approach to disable and enable a kernel preemption. It provides two simple system calls, that is preempt disable and preempt enable, for disabling and enabling kernel preemption. In addition, however, the kernel is preemptable if any kernel mode task to holding a lock. Deadlocks can occur when two or more processes are unable to proceed because each of waiting for other to release a resource. Techniques like resource allocation graphs and deadlocks avoidance algorithm helps to prevent deadlocks. Spin locks along with enabling the disabling kernel preemption are also used in the kernel only when a lock is held for the short duration. When a lock must held for a longer period, semaphores are appropriate for the use. And next one, synchronization in thread. The thread API provides mutex locks, condition variables and read-write locks for thread synchronization. This API is available for programmers and is not a part of a particular kernel. Mutex locks represents the fundamental synchronization technique used in the thread. A mutex locks is used to protect the critical sections of a code, that is a thread acquires the lock before entering a critical sections and release it upon exiting the critical section. Mutex is synchronized primitive used to protect the critical sections and code from a stimulation's execution by multiple threads. Threads acquire a mutex before entering a critical section and release it after completing the critical section. Only one thread can hold a mutex at a time, and others will to wait until it becomes available. Condition variables are used for the thread signaling and synchronization based on a particular conditions. Thread can wait on a condition variable until the another thread signal that that condition is met. That this allows a sleep efficiently while waiting the specific conditions to change a semaphore. Semaphores are synchronization mechanism used to control access to a shared resources with limited number of primitives. They can be used to signaling between threads and limiting the number of threads accessing a resources simultaneously. Barriers synchronize a group of threads by focusing them a wait design point until all threads in the group have reached that point. Once Once all the threads have arrived, the barrier is released and all threads can continue execution. The thread cancel function allows one thread to terminate the execution of another thread. This should be used with a caution as it can lead to resources leaks and inconsistent program states. We provide a programming project at the end of
Atomic transaction, often referred to as atomicity in the context of database and distributed system, are a fundamental concept in computer science and database management. An atomic transaction is a set of one or more operations or tasks that are treated as a single, indivisible unit of work. This means that either all the operations within the transaction are successfully completed or none of them are applied at all. There is no partial execution or inconsistent state. The ACID properties are set of four key characters that define the behavior of atomic transaction. First one, atomicity. As I mentioned above, atomicity ensures that either all the operations within a transaction are executed successfully or none of them are. If any part of the transaction fails, the entire transaction is rolled back and the database returns to its initial state. Second one, consistency. Consistency ensures that database moves from valid state to another valid state after a successful transaction. It means that the data in the database must satisfy all the defined integrity constraints. Third one, isolation. Isolation ensures that each transaction is executed in isolation from other concurrent transactions. This means that the intermediate state of transaction is not visible to other transactions until it is committed. Fourth one, durability. Durability ensures that once a transaction is committed, its changes are permanent and will survive any subsequent failures, such as system errors or power collection of instructions that performs a single logical function is called transaction. A major issue in processing transaction is the preservation of atomicity. Despite the possibility of failures within the computer system, we can think of transaction as a program unit that access and perhaps update various data items that reside on disk within some files. From our point of view, such a transaction is simply a sequence of read and write operations terminated by either commit operation or an operate operation. A commit operation signifies that the transaction has terminated its execution successfully, whereas an abort operation signifies that the transaction has ended its normal execution due to some logical error or a system failure. If terminated transaction has completed its execution successfully, it is committed to; otherwise, it is aborted. Volatile storage. Information residing in volatile storage does not usually survive system crashes. Example of such storage are main and cache memory. Access to volatile storage is extremely fast both because of the speed of the memory access itself and because it is possible to access directly any data item in volatile storage. Non-volatile storage. Information residing in non-volatile storage usually survive system crashes. Example of media for such storage are disks and magnetic tapes. Disks are more reliable than main memory but less reliable than magnetic tapes. Stable storage. Information residing in stable storage is never lost, should be taken with a grain of salt, since theoretically such absolutely cannot be guaranteed. To implement an approximation of such storage, we need to replicate information in several non-volatile storage caches. Log-based recovery. Transaction name, data item name, old value and new value. Checkpoints. When a system failure occurs, we must consult the log to determine those transactions that need to be redone and those that need to be undone. In principle, we need to search the entire log to make these determinations. There are two major drawbacks to this approach. First one, the searching process is time consuming. Most of the transactions that according to our algorithm need to be redone have already actually updated the data that the log says they need to modify. Although redoing the data modification will cause no harm, it will nevertheless cause recovery to take longer. Output all first one output all log record currently residing in volatile storage. Second one, output all modified data residing in volatile storage to the stable storage. Third one, output a log record checkpoint onto stable storage. And for all transaction tk in T such that the record of appears in the log executed redo or executed undo. atomic transactions. We have been considering an environment in which only one transaction can be executing at a time. We now turn to this case where multiple transactions are active simultaneously because each transaction is atomic. The concurrent execution of transaction must be equivalent to the case where these transactions are executed serially in some arbitrary order. This property called serializability can be maintained by simply executing each transaction within a critical section. Stereolability. Consider a system with two data items A and B that are both written by two transactions T0 and T1. Suppose that these transactions are executed automatically in the order T0 followed by T1. This execution sequence, this is called schedule, is represented in figure 6.22. In schedule first of figure 6.22, the sequence of instruction step is in chronologically order from top to bottom, with instruction of T0 appearing in the left column and instruction of T1 appearing in the right column. A schedule in which each transaction is executed automatically is called a serial schedule. A serial schedule consists of a sequence of instructions from various transactions wherein the instruction belonging to a particular transaction appear together. Thus, for a set of n transactions, the existed n different valid serial schedules. Each serial schedule is correct because it is equivalent to the atomic execution of the various participating transactions in some arbitrary order. If we allow two transactions to overlap their execution, then the resulting schedule is no longer serial. A non Consider a scheduler S in which are two consecutive operations OI and OJ of transaction TI and TJ respectively. We say that OI and OJ conflict of they access the same data item and at least one of them is a write operation. To illustrate the concept of conflicting operation, we consider the non-serial schedule to figure 6.23. The write operation of T0 conflict with the read A operation of T1. However, the write A operation of T1 does not conflict with the read B operation of T0 because the two operations access different data items. Let OJ and OJ and OJ be consecutive operations of schedule S. If OI and OJ are operation of different transaction and OI and OJ do not conflict, then we can swap the order of OI and OJ to produce a new schedule S1. We accepted S to be equivalent to S dash as all operations appear in the same order in both schedules except for OI and OJ whose order does not matter. We can illustrate the swapping idea by considering again schedule 2 of figure 6.233 as the write operation of T1 does not conflict with the read B operation of T0. We can swap these operations to generate an equivalent schedule regardless of the initial system state. Both scheduling produce the same final system state. Continuing with this procedure of swapping non-conflicting operation, we get swap the read B operation of T0 with the read A operation of T1. Swap the write B operation of T0 with the write A operation of T1. Swap the write B operation of T0 with the read A operation of T0. Locking protocol. One way to ensure serializability is to associate with each data item a lock and to require the each transaction follow a locking protocol that governs how looks are acquired and released. There are various modes in which a data item can be locked. In this section, we restrict our attention to two modes: shared modes and exclusive modes. Shared. If a transaction TI has obtained a shared mode lock on the data item Q, that TI then read this item but cannot write Q. Exclusive. If transaction T1 has obtained an exclusive mode lock on data item Q, then T1 can both read and write Q. And growing phase, a transaction may obtain locks but may not release any lock. Shrinking phase, a transaction may release locks but may not obtain any new locks. Initially, a transaction is in the growing phase. The transaction acquires locks needed. Once the transaction releases a lock, it enters the shrinking phase and no more lock request can be issued. The two-phase locking protocol ensures conflicts serializability. It does not, however, ensure freedom from deadlock. In addition, It is possible that for a given set of transactions, there are conflict serialization schedules that cannot be obtained by use of the two-page looking protocol. However, to improve performance over two-page looking, we need to either to have additional information about the transaction or to impose some structure or ordering on the set of data. Suppose that transaction Ti is used read queue. If Ts of Ti is smaller than W timestamp, then Ti needs to read value of queue that was already overwritten. Hence, the read operation is rejected and Ti is rolled back. If Ts is greater than W timestamp, then the read operation is executed and R timestamp is to set the maximum of R timestamp and Ts. Suppose that transaction Ti is issue right if Ts is smaller than R timestamp, then the value of Q that is producing was needed previously and Ti is assumed that this value would never be produced. Hence, the write operation is rejected, is rolled back. If Ts is smaller than W timestamp, then Ti is attempting to write an absolutely value of Q. Hence, this write operation is rejected and Ti is rolled back. Otherwise, the write operation is executed. A transaction Ti that is rolled back as a result of the issuing either a read or write operation is assigned a new timestamp and is restarted. To illustrate this protocol, considering a schedule 3 of figure 6.24, which included transaction T2 and T3, we assume that transaction is assigned a timestamp immediately before its first instruction. Thus, in schedule 3, TS is smaller than TS and schedule is possible under the timestamp protocol. This execution can also be produced by the two-page locking protocol. However, some schedules are possible under the two-page locking protocol, but not under the timestamp protocol and vice versa. The timestamp protocol ensures conflict serializability. This capability follows from the fact that conflicting operations are processed in timestamp order. The protocol also ensures freedom from deadlock because no transaction ever
See the summary of this topic. Given a collection of a cooperating sequential processes that share data, mutual exclusion must be provided. One solution is to ensure that a critical section of code is in use by only one process or thread at a time. Different algorithms exist for solving the critical section problems with the assumption that only storage interlock is available. The main disadvantage of these user coded solution is that they all require busy waiting. Semaphores overcome this difficulty. Semaphores can be used to solve various synchronization problems and can be implemented especially if hardware support for atomic operations is available. Various synchronization problems are important mainly because they are example of a large class of concurrency control problems. Monitors provide the synchronization mechanism for sharing abstract data types. A condition variable provides a method which a monitor procedure can block its execution until its signal to continue. OS also provides support for synchronization. For example, Solaris, Windows, XP, and Linux provide mechanisms and such as semaphores, mm, mutex, mutexes, spin locks, and condition variables to control access to shared data. The pthreads API provides support from mutexes and condition variables. A transaction is a program unit that must be executed automatically. That is, either all the operations associated with it are executed to completion or none are performed. To ensure automaticity despite system failure, we can use a write ahead log. All updates are recorded on the log which is kept in stable storage. If system crashes occurs, the information in the log is used to restoring the state of the updating data items, which is accomplished by use of undo and redo operations. To reduce the overheads in searching after log system failure has occurred, we can use checkpoint scheme. To ensure serializability, when the execution of several transactions overlaps, we must use a concurrency control scheme. Various concurrency control schemes ensure serializability by delaying an operation or aborting the transaction that issued the operation. The most common ones are locking protocols and timestamp ordering schemes.